All right, good morning, everyone. My name is Ayrton Coles, and on behalf of our Tennessee Transportation Assistance Program, and on behalf of our Center for Transportation Research Director, Dr. Kevin Hislop, we welcome you to our Rethinking Traffic, How Technology Improves Everyday Travel. We'll be here for the next hour, and I would like to say thank you to our instructor, Dr. William Barber. William is a senior research scientist at the Institute for Software Integrated Systems and adjunct professor at Vanderbilt University. He received his PhD in civil engineering at Vanderbilt University, his master's degree in sustainable and resilient infrastructure systems at the University of Illinois Urbana-Champaign, and his bachelor's in biosystems engineering here at the University of Tennessee in Knoxville. Dr. Barber serves as the engineer and technology lead for the Tennessee Department of Transportation's I-24 Motion Test Bed and Nashville Department of Transportation LADDMS project. His work spans both the physical engineering and implementation of transportation systems, as well as large-scale data analytics, algorithm implementation, and software engineering. His professional mission is to use intelligent transportation systems, solutions, data, and artificial intelligence to improve safety and mobility. So I just would like to tell you that this is a little different setup that we usually have our webinars for TTAP. I will pass the microphone now to our CTR director. He's going to say a few words, and then William is actually going to get us started here.
Thank you, Ayrton. Thank you for all of you that are joining us online through TTAP today. I think this is going to be a really interesting presentation. Talking to our students in the room here, I want you to realize that just like 2 or 3 years ago, Will was sitting in these same seats, right? It was just 2 or 3 years ago you were here, right, Will?
2 or 3. Add 10 to that.
Yeah. But the work that you're doing here at UT, the work that you're building upon right now, you can have the impact that Will's having in Nashville and around the country and around the world. So very excited to have one of our own here, and very excited to hear from him. So thank you for being here.
All right. Thank you all for the warm welcome. It is really, truly a pleasure and honor to be back here at my alma mater. It really has changed a lot since I was here in many, many ways for the better. There's a ton of great work here at UT in the transportation areas. And yeah, I'd like to share some of our perspective from over in Nashville. And I'm going to try today with kind of the overarching goal of weaving some of these projects that we've done over the last, I don't know, 5 years during my time as a research scientist. I'm going to try and weave them all together into this sort of vision for how technology can help us rethink traffic on our roadways. As we talked about in my introduction, I've had a good number of universities that I've been a part of, currently at Vanderbilt University as a senior research scientist. But my career began here at UT. I was over on the ag campus in biosystems engineering, and I had the chance at that during those years to work on some water quality sensing, as well as some tractive power studies for the Army Corps of Engineers. My PhD was in railroad engineering, focusing on optimization and scheduling algorithms. And you know, it's been really recently that I found myself in the ITS realm. So I'm a big believer in the ITS industry and what it can do for transportation. So I hope to get you excited, especially for the students in the room, get you excited about ITS. We constantly hear from students that the reason they didn't get to choose a career focusing on technology and transportation is that they didn't really know about what all opportunities there were out there. So I hope that I illuminate some of those for you today, as well as going to get you inspired and really excited about what we could see in the future. All right, I'm going to start off with a nice graph here. This one's from FHWA. This is showing the cost of road building relative to what it was in 2003 and adjusted for inflation. So the trend of building hard infrastructure, paving our roadways and putting up signage and traffic signals and everything has continued to increase. And that trend has continued a little bit. It's flattened off a bit, but overall, building things out in the world is getting more expensive. And paving a new lane on a roadway is more expensive than it's ever been. What a guiding principle of our work is, what can technology do to increase the capacity of our roadways. Instead of building another lane, which we know is very costly, and we'll end up in this problem of induced demand. You build another lane and that one will get filled up as well. This is a very common theme amongst transportation. Not saying we never need another lane or additional roadway capacity, but what can technology do for us, and maybe do a little bit cheaper than building additional pavement. The other thing, if you've ever taken a traffic flow theory class or a traffic engineering class, you might be familiar with the fundamental diagram in traffic flow theory. This really tells us at a high level that when you put more and more vehicles onto the roadway and those vehicles become separated by smaller and smaller distances, that's traffic density, so the number of vehicles on the roadway for a given area. When traffic density continues to increase, we can maintain kind of free flow speeds for a while, and then we start to see those speeds drop off precipitously. So as we continue adding vehicles to the roadway, we'll eventually see the speed on that roadway kind of fall off a cliff, and we get this kind of congestion that we've all been very frustrated by many, many times. So this is another one of these guiding principles, whether we can kind of use this fundamental relationship in traffic and kind of use this to our advantage. Can we get technology to help us with the fundamental laws of traffic and keep us in our nice free flow speeds where everybody's getting where they need to as quickly as possible, and avoid some of this congestion that everybody finds annoying and that ultimately is unsafe. So we'll talk a little bit about how some of our work fits in there, but these are some of the guiding principles that have kind of motivated this talk. Today's agenda, I'm going to talk about 3 different projects that have happened on the highway in Tennessee, and then I'm going to talk about one that's happening on our urban street network in Nashville. At the very top here, I'll say that I have been involved very deeply in all of these projects. However, these are massive endeavors with a lot of people who are involved. I would have to spend 5 minutes shouting out everybody who has contributed to these projects. The Tennessee Department of Transportation has been an amazing partner in these projects and has really given us opportunities to apply some of these cutting edge techniques to the Tennessee roadways, as well as our partners at Nashville Department of Transportation. They've kind of bought into this vision as well, and wanted to see what technology can do for their roadways. So huge shout out to all of our partners. I would love to mention everybody, but that would take a little while. So over on our highways, first of all, traffic is more complex than we think it is. So we all are familiar with Google Maps and seeing red, yellow, green on the highway, and it's going to be good times until you hit that patch of red up ahead, and we'll start to see congestion. However, that's a vast oversimplification of what traffic actually looks like on the roadway. This video, and I'll play it again here, shows a little bit more of what we might see on the roadway if we kind of had a nice bird's eye view. We see traffic kind of creeping along, and these stop and go patterns of traffic that really make up that kind of slowdown. It's not just everybody crawling along at a nice 40 miles an hour. It's more often stop and go, 0 to 30. And that's both annoying for drivers as well as dangerous. So these complex traffic patterns, we wanted to study these with an instrument that we dreamed up called I-24 Motion. So we don't actually have all that great of data about how our roadways operate with respect to individual vehicles. The data sets for that tell us all of our little vehicle interactions and all these really kind of fine-grained traffic patterns, those data sets are few and far between. So I-24 Motion was our instrument that was designed to collect more of this data, study our roadways in much finer detail than we've been able to before, and ultimately give us solutions for how to improve traffic. I'm going to talk a little bit about the technical development of I-24 Motion because, this being civil engineering, we don't spend all our time on computers. We spend some time out in the field, and there's a lot of engineering effort that goes into actually building a system like this. It's a huge amount in the data center and in code, but there's also a huge amount in the field. So I was kind of out here with the contractors during the building of I-24 Motion and involved in the development since day one. The ITS industry, we know how to hang up a camera to observe traffic. We stick a pole in the ground, you stick some concrete under that pole so it doesn't fall over, you aim the camera at the roadway, and we get this nice view of what traffic looks like. Those cameras, you can pan them around, you can zoom in further down the roadway. And these are really helpful for incident management. And so the traffic management center knows what's going on out on our highways. However, if we're trying to get sort of observability into all of traffic all at the same time, we need a couple more cameras. This one isn't going to cut it. So again, we start with one, and we need to figure out a way to get a few more up there. Well, this is pretty easy. All we have to do is just bolt them on. Why should this be so hard? Well, if we can do that, all we have to do is duct tape them up there, and we'll get this, nice, larger coverage of a patch of roadway from one single camera pole. This will help on cost, so we don't have to install hundreds of these steel poles up and down the roadway. We just have to figure out how to get those cameras up there. We don't use duct tape. We don't even use bolts. This was our very first prototype for actually how to fit 6 cameras up on a single pole. This design did not exactly persist. It was a little bit more fragile than we thought. So we worked with a company down in Alabama to actually make a custom product to hold 6 cameras up on a single camera pole. They're a great partner, and we went through a couple design iterations, and we call this thing the Beetle because it's got 6 legs and holds 6 cameras. But it does a great job of letting us get more pixels on the roadway, use fewer steel poles in order to do that, and let us cover more roadway in this camera coverage. When we're actually getting those poles up, this is quite an endeavor because these aren't small steel structures that we're putting on the roadway. These are 110 to 135 foot tall poles. The 135s for I-24 Motion are actually the tallest in the state for traffic. So this is quite the engineering project as well. If you're wondering why they're 135 feet tall, well, they come in 3 pieces, and that's as much as you can fit on a single flatbed truck without getting an oversized permit. So we asked how tall can we make them, and somebody told us 135 feet. We said, all right, deal. So this is a video of us hanging up the first 3 poles. This was part of our validation system. We then started construction on the full system in 2022. And commissioned all 40 of the poles that are part of the core system. That's 276 cameras across all 40 of those poles. We commissioned that system in late 2022, just in time for one of the other projects I'll talk about here in a little bit. But these are laid out across 4.2 miles of I-24, and there's not a single inch of that roadway that we can't see from one of those cameras at a given time. So here's an aerial shot. Here's just a very small subset. I believe this is 8 of the 40 poles that are out there. So this continues for another 3 miles past this point. So lots of infrastructure out there. And what does it actually give us? Well, it gives us a massive number of camera feeds, of course. This massive number of camera feeds on its own is, a nice visual. However, we care more about what's in that set of camera feeds than we do just kind of putting them up on a board. We could look at this all day, but not be able to actually understand really what's going on in this large composite feed. There's a traffic wave, sort of one of these stop and go waves where people are inching through and being nice and frustrated as they're trying to get into Nashville. There's a traffic wave in this amalgamation of camera feeds here. It's just pretty tough to see. If you have a keen eye, you might see it in a few of these cameras where these vehicles are stopped. But this is not human interpretable. We need a much better way to actually understand this data, and that's where computer vision processing comes in. So we talked about the engineering side, getting these cameras up, and the hardscape and all the materials that go into this. And then there's the cyber side, where we actually pull these data feeds into a data center, and we need to run computer vision tracking on every single object that we can see in all 276 cameras. That is no small feat. We're even making this harder with trying to do this in 3 dimensions. So we try and get the 3-dimensional bounding box of every single vehicle. And that 3-dimensional box is important because we don't really care where approximately in the image the vehicle is. We want to know where its front and rear bumper are, how wide it is, how tall it is, how long it is, and track that really precisely along the roadway. Once we do that computer vision tracking, we actually need to convert that to roadway coordinates. Nobody gives you the roadway coordinate system in all these camera feeds, and they're all looking different ways. We actually need a way to project those detections onto a sort of virtual roadway, so we can kind of get that nice bird's eye view across 4.2 miles of roadway. So that process of getting those vehicles over there onto that virtual roadway involves a lot of calibration of these cameras. This is a process called localization. So detection and tracking of the objects within camera feeds. And then we need to do localization. Where exactly are they on the roadway? Well, we went back and forth with a lot of systems for how to do this and ended up at this brute force solution where we actually put GPS points on the corner of every single road marking on those 4.2 miles. This was a painful process. Nobody had fun doing this. It was interesting for about the first 90 seconds, and then it was a chore. There were, I believe, 12,000 individual points that had to be hand annotated along that roadway. And after we finished doing that, we realized something kind of unfortunate. Steel poles are not rigid. They bend, and they bend because of differential heating in that steel. So if you think back to your material science classes, when you heat up that one side of the pole, you'll get deformation in that side, and the pole will actually kind of lean over, and engineers have characterized this the sunflower effect. Well, this was an unfortunate realization when we realized our nice, calibrated cameras, well, actually, they're not calibrated once the sun comes up. So, the sun goes down, we can't see anything, but the camera's perfectly calibrated. As soon as it's daylight out, our calibration's blown. So we actually had to develop sort of an auto calibration that uses this initial calibration and constantly reevaluates it every second in order to determine how far is the pole leaning over. You can see this is two images superimposed, and our lanes will actually move by half a lane. So we can get a serious shift in where those vehicles would actually be detected. So this is just one of 1,000 really annoying engineering rabbit holes that we had to go down. But we eventually got all this working. And this is actually an early video from kind of what that result is. Once you get all those vehicles correctly localized to the roadway, we can watch every detection. And ultimately, we kind of smooth out these detections. It's a little bit noisy, so we have to massage that data a little bit. But this is what it is after we sort of do that tracking and then localization to a virtual roadway. All right, who students have seen a time-space diagram before? Yeah, okay, good. All right, so for some of you, this will be new. For some, it will not be. Imagine we lay our roadway out on one of our axes of a two-dimensional plot here. So on the vertical axis, I'm going to give you the roadway, sort of a linear, take all the curves out of it, make it a nice line, and put that on your y-axis. Put time on your x-axis, and we're going to plot the position and time of a vehicle as it moves along the roadway. So our little virtual car here, he's cruising right along at 60 miles an hour, and he has these nice uniform spacing of points. He covers the same space in the same amount of time. Delta x, delta t is the same until he reaches a point where he starts slowing down. So in this case, I kind of illustrate this as a lane change, but we kind of lay that roadway out, all lanes kind of in the same plane. But if that car is slowing down or encounters a traffic jam, for instance, we'll see that slope of that line start to bend, and it'll start to flatten out. And in fact, if he completely comes to a stop, we'll see a perfectly flat line because time is advancing and he's going nowhere. So this is how you read one of these time-space diagrams. If he starts up again, then we'll see that line, the slope return to its kind of free flow speed. So we're just measuring slope here, and we can do that for the I-24 motion system. This tiny little diagram up here are some of those trajectories for individual vehicles, except I cropped this photo by basically the amount of data that the traffic flow theory community was using that was of this same quality. So individual vehicle positions over time. This is how much data we are dealing with. So y-axis is space, x-axis is time. So we had about 45 minutes across, I think it was 1,500 feet. So small data set. And this was the first day of I-24 motion on the same scale. So we have 4.2 miles of roadway on the y-axis, and you'll see on the x-axis, we have, in this case, I think about 6 hours. So this is actually morning traffic. What you're going to notice here, all these nice straight green lines here are free flow traffic. And then these red streaks here, we'll examine one of these once this comes to a stop, but these red streaks are traffic waves. So they're moving traffic jams. If you can envision somebody coming to a stop behind you in a traffic jam, and behind them somebody else coming to a stop, and another car and another car, we start to build this queue, and that queue builds backwards along the roadway. So our vehicles are driving in this direction, kind of towards the top right of the image, and our traffic waves are actually traveling in the opposite direction, backwards along the roadway as time advances. These white vehicles are actually probe vehicles from one of our experiments. So you can see kind of individual trajectories highlighted, and you'll see these little bends here where these vehicles had to slow down. So they're going through multiple traffic waves. This would be a very unpleasant commute. Imagine just trying to get through this 4-mile section, and you might be one of these vehicles that has to stop once, twice, 3 times, 4 times, maybe even a 5th. So this is what I-24 looks like southeast of Nashville as folks are trying to commute into work. They're getting stuck in these traffic waves over and over and over again. We'll talk about some of the implications of this in a second, but this is kind of traffic observability in its truest form, and we can find interesting phenomena on the roadway as well. So this is sort of one of those pictures of these traffic waves traveling backwards along the roadway, except something happened this morning. There was a crash. That crash creates a bottleneck on the highway. Vehicles can't get through as quickly as they were able to, so the back of these traffic waves aren't fed with enough vehicles to sustain them, and they start to die off in time. You see this kind of sparse area. There are definitely vehicles going through, but there aren't as many. You can just tell by kind of the density of green there. Well, that crash is cleared at this moment, and all those vehicles rush through that where we previously had a bottleneck. They rush through, and traffic actually returns to this traffic wave state. So we created a bottleneck, choked off the flow, and then as soon as we opened that back up, these traffic waves returned. So this was, we see this quite a bit. In fact, here are a couple other sort of phenomena we've seen. This is just a very low speed rear end crash. However, that causes a lane to be blocked. It causes police activity, and we see these things day in and day out. We can look at months of this data. In fact, we have hundreds of days of it at this point, and we see crashes all over the place. So once you get kind of good at looking at these things, we look at them every single morning as the data is produced. You see crashes without a moment's hesitation. So I-24 is a really rough, dynamic roadway. It's not very pleasant to drive, and this is one of those reasons. So this is all about traffic observability. And let's segue really quickly into the I-24 Smart Corridor. You might be wondering, well, this is fine and good. You observe traffic, you see these phenomena. What do you do about it? So the Tennessee Department of Transportation embarked on the I-24 Smart Corridor project back in, oh gosh, it's been quite a while, I think 2018 kind of era. And this was, their intention here was adding another lane to I-24 was going to cost about $2 billion at the time. So $1 billion per side to add one more lane. If you're wondering why it's so high, well, the roadway slopes off really dramatically on that side. You have to acquire right-of-way property on that side because the roadway is already kind of at max width. You'd have to rebuild bridges and interchanges. It'd be a ton of work to add one more lane to that highway. So can we use technology, again, coming back to our theme, can we use technology to increase the capacity of that roadway, smooth out traffic, make that commute more pleasant for everyone? So that was the overall objective with I-24 Smart Corridor. And the way that we went about that was installing digital message signs along the roadway, and they're actually in these sort of clusters of kind of smaller digital heads. So they're not that full lane spanning message board. They're smaller message boards. These are centered over each lane, and there are 67 of these sets of gantries along the roadway. 30, I think it's 34 in one direction, 33 in the other direction. And these are informing drivers about what the conditions are up on the roadway ahead. So we call this system the variable speed limit system. It's constantly adapting to the state of traffic on I-24 and constantly trying to give drivers the best possible information about what's happening up ahead. This is a pretty complex system to run. It doesn't have nice, clean rules for sort of how you would, or what speed you would want to place on these boards. And you can, the bottleneck could be at any point along the roadway. Traffic could obey a different pattern at any moment. So we actually proposed an AI algorithm to run this system. So this is hard infrastructure being run by an AI algorithm in the background. So we wrote this software to implement this AI algorithm in 2021 and 2022. And it went live in early 2023. So what I'm going to show you today are kind of the results from that deployment and what positive effect, if any, it had on the roadway. Spoiler alert, it was positive. Otherwise, I probably wouldn't be talking about it today. But this has been a really great project by the Tennessee Department of Transportation because it achieved the exact objectives it was set out to do. So you've seen this photo before. Here are all of our I-24 motion poles, or 8 of them at least. Well, here's one of those gantries inside of that I-24 motion system. So these two systems overlap. I-24 Smart Corridor is like 30 miles long. I-24 motion is only 4. But the co-location of these two systems gives us some interesting opportunities. You remember this photo as well. Here are our traffic waves. Well, you might have noticed these things all look pretty similar. Again, they're traveling backwards along the roadway, but they appear to be doing it at roughly the same speed. This was an insight that we used to help tune this variable speed limit system. These traffic waves are actually very predictable. They go backwards along the roadway at about 12 miles per hour. The range is like 11 to 15, but the mean is about 12. And that 12 miles per hour equates to going from one gantry to the other. They're spaced at a half-mile apart, going from one gantry to the other in about 2.5 minutes. So if we just know where that traffic wave is going to be in 2.5 minutes, then we can start to kind of be proactive about some of these potentially dangerous traffic waves. People could be cruising along at 80 miles an hour and come upon one of these things, and if they're not paying enough attention, they don't hit their brakes hard enough, they could cause a rear-end crash. So these traffic waves are worth notifying drivers about, but they happen really quickly, and we have to make really fast decisions about what to do. So we have to keep the variable speed limit system really responsive to these conditions. And we use an AI technique called multi-agent reinforcement learning. I will save you the math of how all this works today. If you're curious, we can go find a whiteboard after the talk. But I'll give you the high level here. And that is that we have a reinforcement learning agent. We said multi-agent, so there's going to be more than one, but we'll have one for this variable speed limit gantry here. That gantry is going to tell drivers at this location what traffic conditions are roughly up ahead. And we can't just tell them, all right, well, you're going 80 miles an hour, you should be prepared to go 30 miles an hour in just a quarter of a mile. So we have to enforce some kind of patterns to this and make sure that we give drivers enough advance notice. So that multi-agent reinforcement, or that reinforcement learning agent, is responsible for posting a speed limit on that gantry right there. And it's actually going to look at traffic conditions up ahead of where it's posting that message. And so we kind of run these step by step, and each agent in the multi-agent reinforcement learning kind of setup here is responsible for its single gantry. And so they're all looking at both each other as well as traffic conditions. So we can do this over and over and over again, 67 times. It takes, I think, about 20 milliseconds for this to run. It took hundreds of hours of training and simulation for it to get to this point, but once it knows kind of what it's expected to do, we just feed it data, and then 20 milliseconds later, it gives us an output, which is what the speed limit should be for each one of these gantries. As you're driving through, it'll look something like this. This vehicle's cruising right along, and suddenly we start to see those speed limits drop. So it was 70, then you saw that 60, 50, 40, and we're still cruising at this point. Here you see a 30, but again, we're trying to warn drivers what's up ahead, and sure enough, we start to get into this congestion pattern. The stop and go traffic, it's sped up really fast, so it still looks like traffic is moving right along, but this is stop and go. And then we'll sort of speed right back up after we exit that period of congestion. So we drove this 100 times or so to make sure it actually worked. There's a ton of data analysis to make sure the system was reporting accurately. The worst thing you could do here is make drivers not believe this system, for them to lose confidence and trust in the system. We rely on them knowing that when they see that speed start to drop, they need to start paying attention. That's how the system works. To date, the multi-agent reinforcement learning algorithm in this software has made over 100 million decisions. Every 30 seconds, it updates. It takes in data every 30 seconds, produces what speed should be posted for each one of those iterations, and tens of millions of people have driven through this corridor in that time.
Is the speeds uniform by lane, or will
There is the ability to do different lane by lane, but as a policy, the system was kind of designed that with the expectation that we're going to uniform across the lanes. That's not the case everywhere, especially if you have like a strong HOV lane or a managed lane or something, then they'll differentiate. But on this roadway, we figured it was enough signal already to drivers. So yeah, they'll be uniform across the 4 lanes here. All right. So you might be wondering, well, you do all this nice AI engineering and you put all this infrastructure out there. Well, how did it actually affect drivers and how did it improve that roadway? Well, first off, I need to begin with a caveat. This system, it is sort of, we call it active. When it's active, when it's telling drivers that the speed is sort of below the free flow speed. So it's default 70 miles per hour. Anytime it's less than 70 miles per hour, we're going to call it active. Anytime it's right at its default of 70, we're going to call it inactive. When there's no traffic, we're telling drivers that conditions are fine. You can sort of go the speed limit. It's there's nothing obstructing you, and there's sort of nothing that the variable speed limit system can do to stop a crash during free flow conditions. So we're going to ignore the times when the system is inactive and drivers run off the road for whatever inexplicable reason, and we're going to look at VSL effectiveness when the system is actually operational during congestion. So here's a summary of the results. Traffic on I-24 is actually up. While we were doing this project, the volume on this roadway continued to rise. We kind of didn't think it could rise anymore. We kind of thought, well, it's at capacity. Well, during that time, the demand went up. So we're up about 6.6%. This is a pretty dramatic increase for a roadway that's already pretty saturated. At the same time, secondary crashes, meaning when there's already a crash out on the roadway and then another crash happens behind it because drivers aren't expecting to slow down, that's a secondary crash. Those crashes are down 50%. And one of the reasons is because drivers are getting that advance warning. If you're not using Google or something that's showing you, hey, there's a crash up ahead, you might not know and you're not expecting that slowdown. So secondary crashes are down by half while VSL is running. And overall, while VSL is running, the crash rate overall is down by 14%. Very importantly, for other roadways of similar characteristics around Nashville, crashes are up around 12 to 14% on other roadways. So reasonably, we could actually expect that crashes would have increased by a significant amount, over 10% during the same time, but instead we saw them decrease pretty significantly on I-24. So the difference between those sort of expectations is around 24% on net. But overall, this is decreasing crashes while every other roadway has the trend going in the opposite direction. There are a couple other side benefits here. The Traffic Management Center is actually seeing crashes earlier because of how VSL is alerting them to speeds decreasing. We're finding more events, so more crashes, more slowdowns, more stalled vehicles. We're finding more from the TMC because of the observability on the roadway, and we're doing so faster. So overall, the variable speed limit system has been very effective out here. I don't have time to go into the other side of this coin, which is the lane control system. But those speed limit gantries are also used to tell drivers that a lane is closed up ahead when something like a stalled vehicle is in one of the lanes, and they can sort of proactively start to move over. So this has also helped our first responders feel maybe a little bit more safe out there while lanes are being closed on an active highway. All right, 2 down, 2 to go. So these things are starting to weave together. And now I'm going to jump over to the vehicle side. So this has all been hard infrastructure so far, but our traffic stream is made up of individual vehicles. What can we do from the vehicle side? I'm going to show a video of that same variable speed limit system again, seeing all these pieces tie together. And what happens when a vehicle actually goes the posted speed limit based on the variable speed limit system. All right, so we are driving on I-24 westbound towards Nashville. The sort of character here is this particular truck. When the car we're filming from starts slowing down to obey the variable speed limit system, this truck goes by kind of in a rage, maybe gave us a choice finger on the way by, saying, well, why are you going so slow? Traffic is fine. Well, just wait a little bit. And again, this variable speed limit system is reflecting traffic conditions up ahead. And in fact, look who we come up on the bumper of. That same truck that made an aggressive lane change and was all pissed off that we weren't going fast enough. Well, we catch right back up to him into this traffic wave. So we're in stop and go traffic, and sure enough, we catch right back up. This is the exact same principle that you've probably done at a stoplight before. You have a red light, and you got nice clear space ahead of you, and you say, well, why am I going to rush up to that red light just to come to a stop? Well, instead, you kind of back off a little bit, start braking early, and hope that you can kind of catch that light right as it turns green, or maybe get on the bumper of the person ahead of you without coming to a complete stop. It's the same principle, and we actually set out to kind of implement this principle on individual vehicles. So the variable speed limit system is great. It's informing us of traffic conditions up ahead, and drivers could go ahead and drive this themselves, but we could also get our vehicles to do this. Does anybody have a car with adaptive cruise control, one that kind of monitors the space to the vehicle ahead of you? Yeah, so it'll automatically control your speed based on what the vehicle ahead of you is doing to make sure that you're following at a safe distance. Well, these adaptive cruise control systems, we can actually hack these a little bit. And instead of going the set point that you set using your steering wheel, why don't we just make it go the exact speed that the variable speed limit system says? So the variable speed limits are telling us what are our traffic conditions. Well, if we just drive at the average speed of traffic up ahead, then we can kind of do this rolling stop kind of thing, come right to the back of the traffic wave as it's kind of dissipating. And the hope here is that we can start to dissipate these traffic waves. That if enough people do something like this, then we could actually make that traffic wave go away and kind of pace traffic in a reasonable way. So this is kind of an example of what that looks like. We've got our control car here in blue. It's looking at the speed of traffic around it, and it also gets the data feed from the variable speed limit system. What is my actual speed limit up ahead? Well, we don't follow exactly the speed limit. We actually do something that's a little bit in between. We call this the middle way, and somebody got really creative with the name of a paper and called it the middle way to traffic enlightenment. All right, I'm not here to debate the veracity of that title, but the middle way is a good characterization of what this is, because we're basically going to infrastructure speed, except when traffic around us is going really fast. We don't exactly want people giving us the middle finger all day, so we're going to sort of split the difference. If traffic around us is going way faster, we're going to speed up a little bit, just so that we're maintaining kind of safe control around that and not encouraging people to make dangerous moves. So that's that middle way. And when we run this, I won't spend too much time here, but this black line is basically the actual vehicle's velocity. The green line is traffic speed around it. And then that red line is what the variable speed limit system said. So we're basically controlling this vehicle just inside of what the variable speed limits are and what traffic is doing. So we're splitting the difference here. This is the middle way, and it has been shown to dissipate some of these traffic waves. When we're coming up on the end of traffic, we have an effect on the vehicles around us. When we're slowing down, the vehicles around us decide, all right, maybe I should slow down a little bit, or maybe they're behind us and they can't speed up. So this is having an effect on more than just one vehicle. We call this effective compliance. If you have 10% of vehicles that were doing this, then they would actually have that same effect on 90% of traffic, because those 90% just can't get around even if they wanted to. A few of them can kind of leak through and weave their way, but this difference between actual compliance and effective compliance is something that we can leverage. We only need 10% of drivers to do something in order to sort of have the whole system do that exact same thing. And now we get to a practical application of that principle. We ran the Circles experiment, a consortium of universities, vehicle makers, Tennessee Department of Transportation, and other private sector partners. We ran this experiment in 2022. This is putting that principle into practice. Take stock adaptive cruise control vehicles, tell them what the conditions of traffic are up ahead, and have them mixed into traffic and sort of applying these traffic smoothing principles. Do exactly the same thing that a human would do, where they're trying to kind of roll through a traffic jam instead of race up and stop. And we're going to do this for 100 vehicles out on the roadway, because we need a few of them out there constantly in traffic to have an effect on the ones around them. So We actually implemented this on 100 Nissan vehicles that we got from the factory in Nashville. They were gracious enough to lend us vehicles for a week, or actually 2 or 3 weeks. We installed some hardware that basically allowed us to use their adaptive cruise control system and constantly change the set point of that adaptive cruise control system. We could also change the following distance between the two vehicles. So we have a couple levers to work with here. We designed a cloud system that runs and looks at traffic conditions up ahead and gives those traffic conditions to the vehicles as kind of their desired speed profile. So we put all these cars out onto I-24. So we had 100 drivers. These cars aren't fully autonomous. This isn't Waymo. This is 2022. And so we got 100 drivers in all 100 of those cars, put them out on I-24, and they were driving laps around the interstate. We added those 100 vehicles to the traffic stream with the intention to kind of smooth out these traffic waves that we knew were out there because of our system with I-24 motion. So this is putting into practice these principles that make a lot of sense, but the problem is it's tough to do at scale. So this was one day of that experiment. It was a huge undertaking. It took like 100 staff just to make this happen, plus the 100 drivers. There were a ton of like different departments to the experiment, somebody designing the algorithms, others working on the databases. But it was a huge undertaking. But ultimately, these drivers went out there, smoothed out traffic waves, and actually decreased the overall fuel consumption of the roadway. I forget the exact statistics there. It was a lot of data analysis to actually tell what effect they had on the entire roadway. But it was a positive effect. They killed multiple traffic waves. So those traffic waves where we would expect them to just continue were actually fully dissipated. And then there were other situations where those traffic waves were kind of alleviated. And instead of coming to a hard braking event and then re-accelerating, we're kind of able to slow roll that traffic wave, and might not have gone away completely, but we reduce fuel consumption of the overall traffic stream and also improve safety. So I think the fuel consumption gains here were something like 5 to 10%, which doesn't seem like a lot, but this is tens of thousands of vehicles driving through here. Okay, vehicle side, highway side, we're going to transition to the urban street network now. I promise all these things kind of weave together a little bit. So here we see time-space diagrams. I'm sure everybody has had the opportunity to drive on one of these roadways that gives you that nice green wave. If you're kind of commuting in one direction, you'll see the lights kind of turn green right as you're starting to approach them. This is a very common signal coordination technique called a green wave, or that's kind of the colloquial term for it. And this has been implemented for years. Since we were able to synchronize the clocks of these traffic signal controllers, we could do something like this. One of the problems here is that it's very tough to do this constantly and for changing traffic conditions. These are systems that we might call adaptive traffic signaling. That adaptive traffic signaling is a hard problem because we get random arrivals of vehicles from different side streets, and ultimately, this is just a tough signal strategy to implement. However, better signal timing comes from better data. This has always been true. If we know better the flows of vehicles on different approaches for the roadway, we can better tune the system to give the appropriate amount of green time to all of those demands. I will submit today as a hypothesis that excellent signal timing and coordination, something that's truly adaptive, that's kind of working ahead of where traffic actually is, can come from excellent data. And I'm going to show you what I mean by excellent data, kind of inspired by some of the work that we've done with National Department of Transportation over the last couple of years. Additionally, from the data side, better safety comes from better data as well. We can adapt our roadways for vulnerable road users, pedestrians, cyclists, transit users in the ways that they actually want. So where are they crossing a roadway right now, and how can we make that more safe based on kind of their revealed preferences? That's just a way that we can make those roadways work better for those road users. Additionally, there are a lot of crashes that are almost crashes. I'm sure some of us have actually been in some of those, unfortunately. You might have even had a kind of close call with a vehicle as a pedestrian, especially in pedestrian heavy areas like a college campus. There are just a lot of opportunities for those sorts of things. Well, it's great that those did not actually happen as crashes. However, we would call that a near miss. And that near miss is a very intuitive concept. It's sort of an indicator that there is a safety problem, It might not be showing in kind of the crash statistics, but this is showing that there is a problem that should ideally be addressed, maybe by just some subtle changes. But these are kind of tough to find because nobody files police reports for near misses. So with better data, we can maybe expose some of these patterns on our roadway. All right, the technology that we've been using for this, and I will preface this with, this is not the only technology that would be appropriate for something like excellent traffic signal observability and near miss detection. There are other technologies that do this and can do this very well. But one of the things we've been working a lot with is LiDAR in the ITS realm. So in intelligent transportation systems, we've got lots of different sensor types. LiDAR is kind of a new entrant to the ITS detection space. LiDAR has been used for many years on sort of high-level sensing or terrain detection. The Tennessee Department of Transportation actually flies planes with LiDAR on them to get the topography of the entire state. They fly different counties and zones every single year. And we can do this to scan urban areas and such. Automated vehicles also use LiDAR technology. So one of the reasons they really like LiDAR is that it creates a nice three-dimensional picture of the roadway constantly. And it does this because each laser that it's sending out as a sensing point actually gets an exact distance when it returns. So they're scanning a laser, actually they're scanning 128 lasers constantly around in a circle, and they're building this 3D map of the world constantly. So it's very helpful for an automated vehicle that needs to understand the spatial relationships between things on the roadway. But we can also use this in an ITS context. So we stick a couple of these LiDAR sensors up on our traffic signal poles at an intersection, and we can get a perfect 3D view of what that intersection actually looks like. Within that 3D view, we can detect objects. We can detect vehicles, pedestrians, cyclists, scooter riders with pretty good precision. These LiDAR devices have come a really, really long way in the last few years, and they're really powerful for the ITS context. This is what that 3D view kind of looks like. It's a little tough to see, but you can actually kind of make out the outline of a bus. Because they're getting kind of again, a nice like spatial representation of the world, not just a flat image, it's very easy to see dimensions of things. So you see a few vehicles here, and then this little cluster of orange dots over here is a pedestrian. So this is a view of what one of these intersections might look like from the perspective of a LiDAR device. All right, and because we're getting detections of vehicles and all road users, we can use those to track those objects. If we track those across an intersection, then we'll get thousands of little traces of vehicles making turning movements and crossing the intersection. And these trajectories are really helpful for analyzing things for engineering purposes. Do we need a stop sign at this location? In fact, I believe we just finished up the analytics for this one recently. They were saying, oh, we definitely need a stop sign here. We just need to count the vehicles and all the turning movements and everything. Well, it turns out actually there wasn't enough volume to justify a stop sign there. So, but anyway, you can collect thousands of vehicle trajectories pretty easily. And we can also, so from that, we get our turning movements, we get speeds, we get crosswalk usage for pedestrians. We can also get signal performance metrics. How many people arrived on the red light? How much time did they have to wait? This is really, really powerful data. And these also detect near misses. So in this case, we see in red a pedestrian crossing the roadway outside of a crosswalk and a vehicle crossing right after them. Maybe they saw that pedestrian, but it was a pretty close call nonetheless. And this kind of reveals in a couple of these different patterns what some of these near misses look like. All right. We also installed LiDAR on a mobile trailer that we tow around town, looking at different areas that the city wants to investigate. One of those areas was leading up to an interstate. And again, you see these nice time-space diagrams. These are ones that look more like a signal that's constantly cycling. You see this section of red followed by a section of green. That's vehicles arriving at a signal, getting queued up one after another, and then getting released. So we were studying the interstate on-ramp here and trying to adjust that signal a little bit. Well, let's jump ahead to something kind of recent. I did not come up with this name. It's a little bit silly, but hey, it's fun. Downtown Nashville is a fun place. We have Lower Broadway there. That is a pretty wild roadway. If you've ever visited Nashville during a special event, Broadway is just completely crazy. That is a good problem. It's definitely a management challenge, but would you rather have downtown bustling with activity, or would you rather have it kind of slow and dead? So we definitely lean into the bustling and eventful kind of side of this. But we also have this problem where we have too many pedestrians for the infrastructure. Just as we don't build roadways for peak hour flows, we don't build sidewalks for special events. We just don't. They're not big enough. Downtown Broadway, Broadway, the roadway in downtown alone will have 100,000 people on it during a special event. Sort of downtown Nashville on its own will have peak crowds of over 300,000 people. The July 4th fireworks show this year had 360,000 people in downtown Nashville. They shut down a portion of the interstate because in the last year, people would actually stop on the interstate to watch the fireworks, and they're like, that's a bad idea. So they actually shut it down and didn't allow anybody up there. But this is CMA Fest. There's this absolute sea of people. It kind of looks like a zombie apocalypse in a way. And it's tough to measure too. All those people, they don't really show up on Google Maps. This is traffic, but I guarantee you it's not actually moving nice and free. It's probably having a tough time with the thousands and thousands of phones that are reporting various movements down there. So this sort of data source isn't super great for what our pedestrian volumes look like and how we can best manage something complex like this. And helicopter flights are also really expensive. So helicopters are a great way to get a view of the roadway. If anybody has seen this clip, this is when Vanderbilt beat Alabama. Yeah, it's a year later. We're still showing this. We're very proud of it. Couldn't get the repeat, but we gave it a good shot. But this is in 2024. The police let them carry this all the way down to the river. Had to try and mirror our friends in Knoxville. So it's a Tennessee thing. We tear down goalposts and throw them in rivers. So anyway, this is another kind of zombie apocalypse moment. It's especially in the kind of night vision. It's just almost a little bit scary. They're climbing on cars and stuff. It was wild. Anyway, that's a little tough to get a helicopter up there for every night on Broadway. So we started installing LiDAR on Broadway. Here's a shot of somebody from the National Department of Transportation getting that sensor up on one of these signal poles. So we did this across 5 intersections, installed 10 LiDAR scanners, networked these back to these traffic cabinets that are already out there, got these on the fiber network. This is us kind of calibrating a couple of these sensors in the field, and we get this 3D representation of what Broadway looks like. Well, we don't really care where the buildings are as much as we care where all the people are. So this is the overhead view of one of those intersections as soon as we installed it. A couple hundred people through an intersection, not super crazy for Broadway. That's normal traffic. And vehicles that sit at stoplights for 30 seconds, that's normal traffic for Broadway. And once we installed all this, we actually needed to know if it worked. So we flew a drone through here, and at the same time, we're actually overlaying the LiDAR data. This is not computer vision in this rendering. This is actually LiDAR data that was calibrated to this drone flight using a lot of really weird like special effects processing. But the way that we're kind of not faking it with computer vision is that we see detections for vehicles and pedestrians that are actually on the side street where the drone can't even see them. And so this was kind of our validation for this, and also makes a nice kind of promotional video as well for what LiDAR can do. So we see people on the mid-block areas, even though our sensors are installed here at an intersection, we're seeing people between the intersections as well. We're using longer range scanners to make sure that we can get a full picture of the roadway. And we built this software that actually lets us observe this picture of what the roadway is doing kind of from a top-down perspective. Inspired by that 3D representation of a single intersection, we did a 3D representation of the entire roadway. This also works for all of our other installations around Nashville. And in this case, we're actually replaying this from a database. So we record all this data. It's a lot of data, but we spent a lot of money on database servers. And so it's possible. We're running this at 16 times real time. And at about 16x, you can really see some of the patterns emerge here. You can see the left and right turns operating, and we can see how many vehicles are able to get through on one of these phases of the traffic signal. So this kind of ultra fast replay, you can't run this in real time, of course, because we can't get data faster than we can show it. But after the fact, we can learn a lot about how the roadway operated when we replay data like this. It's also very useful from an operational standpoint in a traffic management center, seeing your kind of overhead view of what Broadway looks like, as opposed to trying to kind of assemble the picture in your head based on a bunch of separate traffic cameras. This is sort of a new capability. So I'm hoping that this very new capability we can kind of roll out for the next generation of traffic signaling in our cities. So again, this is not the only technology that can do things like this. It is one of 3 or 4 that produce this level of data. But if we can start to blanket our cities in this kind of coverage, then it opens up a whole new realm of what we can do for traffic signaling. Today, we rely on patterns. Well, we could in the future potentially have AI that just constantly adapts the signal system based on all the data that it's seeing citywide. That's a very tall order. That's years and years down the road if it ever happens. But I'm kind of confident, or at least hopeful for a future like this, where we can use really excellent, rich data sources like this to kind of usher us into the next generation of transportation. So with that, I managed to weave together 4 different projects. Sorry for going fast on this, but this is kind of a broad vision for potentially what we could see in the next generation of traffic that I hope some of you will be working on yourselves. Thank you for your time.
So William, we had one question here in the Zoom. When you go back to your variable speed limit signs, did you have any enforcement in that? And were you able to analyze what is the impact of enforcement on the roadway?
Yeah, so I'll first say that the variable speed limits are legally enforceable. There's not much enforcement occurring for them. The unfortunate thing is that it's really dangerous for law enforcement to try to enforce those speed limits during congestion. Traffic is speeding up and slowing down really dynamically. Putting a police officer on the side of the road where people are going to try and get away. We have a move over law in Tennessee, so you basically close a lane when you put a police officer out there giving a ticket. So it's a tough problem. So we haven't really relied too heavily on enforcement. That's a legitimate question about whether that would work even better with some additional enforcement. However, it's just really a challenge to do so out there. So far, we've just been relying on people kind of getting habituated to the pattern of the roadway and seeing that these speed limits actually do reflect traffic conditions.
All right, I don't see any additional questions here. Let me see if I find one comment. Just want to mention that to you. If anybody else here in the room have any questions, can go ahead and ask him.
Yeah.
Is not or any other state are they like about? Have you heard about
Yeah, we were asking the same question. The VSL system is very infrastructure intensive. That system costs, I think, over about $100 million. I mean, it's not a cheap system. When you compare it to the $2 billion to add more capacity, or actually they're doing a choice lane project now that's estimated more towards $5 billion. It's a bit of a bargain, but it can only take you so far. That infrastructure intensity, it's a valid question whether you think, could we virtualize that on phones and on vehicles and on dashboards instead of putting up $100,000 gantries instead. We have done a little bit of work with putting that on an app for drivers. And this is kind of part of the connected vehicles realm where you want vehicles and drivers to have the information from your infrastructure. That's probably the more likely path forward, given that you could really scale this up nationwide. If it's a phone-based thing, it's a lot harder to scale it nationwide if you got to put gantries every half mile. So there's still a role for that. For example, in Colorado, they deal a lot with like snow on the roadways and stuff. Well, you can't expect people to have an app on their phone. You're just always going to need to be able to tell them, hey, there's ice on the road. This is dangerous. Seriously, you need to slow down. So there will always be a role for infrastructure, but it's tough to scale.
So just a couple of thoughts and comments. One is about the circles. So one question is, if you had a robo-taxi instead of what you were showing, like you mentioned, alluded to it, like, Waymo now has robo-taxis going on in urban areas in San Francisco and for other towns. So question is, okay, going from adaptive, well, you had adaptive cruise control, right?
Right.
So cooperative adaptive cruise control and then on to robo taxi level 4 type vehicle. How would your results be different, or would they be different?
Yeah, I think we won't know until we try, and I say that in in a hopeful way. I hope that others want to try a system like that, where we get increasing levels of automation to try out these traffic control strategies. The driving strategy here is very simple. If you know the speed conditions up ahead for a given area, go the average speed limit. Go the space mean speed of that roadway segment, and you will smooth out traffic waves. The algorithm is not complex, so they can implement this with sufficient data. Getting that data really clean, really high resolution is a challenging problem. We've shown that probe data alone, the commercially available probe data, is not, it sort of has a latency that's unacceptable for this really dynamic traffic conditions. But these more computerized cars have the ability to incorporate richer and richer data for that longitudinal control. So,
Thank you.
Yeah.
One quick other question is regarding, like you said, they were cutting in, like if the car is going at a slower speed. Did you do any analysis of the volatility or the kind of movements that might be getting too close, or so
well, and this goes, I think, somewhat back to some of our earlier work on whether these sorts of longitudinal control systems, your adaptive cruise control, cooperative adaptive cruise control, even infrastructure guided cruise control, those sorts of systems, we need to know whether they're actually stable. And by stable, I mean, if somebody cuts you off, does that actually create a traffic wave? It would be really bad if putting more computerization out there, putting more control actually made the problem worse. We just spawned a bunch of traffic waves. We don't believe that has to be the case, but everybody who's implementing these systems has to choose an algorithm that is string stable, and by that it means it can absorb a perturbation in the speed or a cut in, like you're saying. So designing those systems is not trivial. Telling them what the conditions are up ahead and what they should do, that's arguably an easier problem than the very safety critical, you must not crash and you must not create dangerous conditions for the drivers behind you. It's an area of active study, and I know some of the regulators are getting more involved in looking at these systems more rigorously.
About the IO part, it's something that have you trained it on like a synthetic or simulated data first, and then gradually adapting as the real world traffics are being recorded?
You're talking about for the variable speed limit system?
Yes.
Yeah. So it was trained in simulation originally. That on its own is a major part of one of our students' dissertations. It's not an easy process, but we've gone through now, I believe, 5 generations of the algorithm. The original one was sort of not responsive enough and kind of not acting dynamically enough. We're able to tune this over time by observing what it does in actual traffic and continuing to kind of fine tune that AI. It's not a feedback kind of loop itself. It's not self-learning over time, but really we're kind of doing human supervised evolution of that AI. So
there's like by living more real data.
Precisely, yeah. So the simulations especially help you a lot with varying traffic conditions to explore a wide range of situations. But when you're transitioning to another roadway with a different number of lanes with different dynamics, there is some degree of retraining or adaptation that's going to be needed. It's not perfectly transferable to all roadways. Kevin?
How much would you estimate has been invested in these 4 lines?
Oh man,
Question is how much has been invested overall?
that's a tough question. Well, I'll take it piece by piece because clearly I can't sum up 4 numbers in my head. So I-24 Motion was funded through state and federal funding that totaled, I believe, about $11 million for the full system build out and everything. Don't quote me on the exact numbers, but somewhere in the ballpark. And the operation of that system does incur some maintenance costs and things like that. The smart corridor, of course, is a large infrastructure project, but an ATC-MTD grant funded the development of the AIDSS, the variable speed limit AI. I don't remember the exact numbers on that. So yeah, I mean, public, like full dollars for infrastructure, I mean, we're over 100 million. But these are very large systems. We didn't build the gantries, but we focus on the software. So ITS does have a cost on its own. I earlier is saying roads are expensive to build, and they are, but I don't want to ignore the fact that ITS can also be expensive. And blanketing a city in coverage of high resolution sensing is an expensive proposition. And the cost of these things will continue to come down, but I think it is kind of right sizing the problem here, and we continue to learn more lessons by trying these things out.
And this work is super impressive. What I want us to know here is it takes a lot to get there.
Oh yeah.
You all have done great with the investment you've had, but the process that you detailed quite well is super. It takes a long time.
Yeah.
A lot of building, a lot of investment.
Yeah, and I want to further emphasize that, like, again, there are hundreds of people involved in the 4 projects I outlined. Nobody does anything alone, especially when it comes to large-scale infrastructure and large systems. So a huge, great team behind all of these different projects.
Hey, Will, I know that we're probably getting ready to leave here, but just one more question. Not only involve a lot of people, but involve a lot of agencies,
Yeah.
right? So can you elaborate a little bit on how Vanderbilt and you guys got to the point where you're able to involve different cities, different agencies, talking to the IT people and all of those things? So if you can elaborate a little bit on that.
Yeah, our research partners in the public sector have been amazingly, innovative to support these projects, and I think there's a lot of trust built up by years of working together. But it is still tough to overcome some of these hurdles. I think IT is a major one. Our infrastructure is under threat from a cybersecurity standpoint, so we have to be increasingly cautious about how we do these things. And IT might have a little bit of a reputation for saying no, but they're saying they're expressing caution in the face of a significant threat. So maybe from the IT perspective, that one especially, we actually circumvent that problem when we can. So sometimes, when we get into network topology and everything, we don't always need to connect everything to every other thing. The I-24 Motion system in networking terms is an island. It has one bridge, which is a nice expensive firewall appliance. But if somebody wanted to hack I-24 Motion, there's one way to get into it. So it's one of these things. It's not connected to every other critical system on the network. And moreover, the exposure to TDOT is more or less zero because it's actually connected to our network as sort of that bridge. So I think working with some of the sort of sub agencies like your IT organizations, looking for the creative solution, which isn't necessarily the most obvious, is sometimes a way to just kind of circumvent the problem instead of trying to run through the wall of advanced cybersecurity on every single point. So I think that's one aspect. And then, on sort of broader public agency work, we really enjoy learning from the public agencies and having them tell us, what are your concerns? What does your world look like? How can we best support? And then the information exchange in the other direction. We do a lot of training with the National Department of Transportation and with TDOT. They help us, they train us, and we help train them as well. So by constantly having that back and forth, I think it both builds trust and also helps get everybody on the same page. Especially with the LiDAR stuff. It's a kind of cutting edge technology. Not a lot of people had exposure to it. Well, it's not as scary once you start exposing people to it. It's not as difficult once you start exposing people to it. So I think, some of that, it's a lot of work to build that trust over time. But I think, very fortunate in our public sector partners' willingness to give us a shot and hear us out on these things.
Well, thank you again. I just would like to say thank you to the 100 plus people that participated online. So thank you for everybody participating. I will end the session here online, and I'll talk to you guys next time. Thank you.